So the next thing that we want to talk about are catalyst. We were looking at factors affecting rates of reaction. We looked at concentration. We looked at nature of reaction, concentration, temperature, and radiation we had seen. Then we also have to look at catalyst and the effect of catalyst on rates of reaction. So we can actually relate it to the graph that we had studied earlier. So we already know the graph for the reactants and products in terms of the energy changes associated with it. This would be a regular graph for a reaction. We have seen threshold energy, the energy barrier, and we know how to calculate the energy of activation. And so here, this is the value for the energy of the uncatalyzed reaction. So we're going to distinguish between a catalyzed reaction and an uncatalyzed reaction. So if you actually use a catalyst, what really happens is the graph changes a little bit, whereby the energy barrier gets lowered or the threshold energy becomes lesser. And now we have a smaller quantity for the energy of activation. So this is a shorter value. So the threshold energy for the catalyzed reaction, the difference between that energy and the reactants is smaller. Therefore, the reaction tends to take place faster, or we expend less energy for the reaction to produce products. So there is a gain in the cost of production because we're not going to waste energy here. So we can use catalysts to alter the rate of reaction by altering the energy of activation that it requires for the particular reaction, and thereby making the reaction more efficient, energy efficient, and cost effective. These are some of the things that we can do. So fundamentally, this is what you have every time you add a catalyst. So we also need to define what a catalyst. So we can say, generally speaking, a substance that alters the rate of the reaction. And when we use the word alters, here we are implying that it lowers the energy of activation, therefore the reaction goes faster. In certain cases, we do not want a reaction to take place, then the forward reaction will not take place at all, or probably we are increasing the energy of activation. So chemicals which we do not want to undergo decomposition and we want them to be stable for a longer period of time, we may add a catalyst which we call a negative catalyst. So catalyst can be positive catalyst or negative catalyst. If it's a positive catalyst, it's going to lower the energy of activation and make the reaction go faster. So that's a generalization of the general idea behind catalyst. And it would be a good idea to come up with some examples of catalyst. Okay. So again, here it's an exothermic reaction. Now here I've just put an arrow here, and that shows the energy difference between the threshold energy for the uncatalyzed reaction and the energy of the products. So in this case, if you calculate that value, you find it's pretty large. It's larger than the energy of activation for the forward reaction. So if you were to change the products back to the reactants, the energy that the products should be supplied with so that it achieves the threshold energy for the reactants to change back into reactants is what we have here. That's the energy of activation for the backward reaction. Okay, so we have reactants changing into products, and we can also have products changing back into reactants if we have reversible reactions. So we will talk about energy of activation for the forward direction. We will talk about energy of activation for the backward direction. And we can look at those values and say which is more stable. Reactants changing to products, and the products will remain stable because the backward energy of activation is larger. Or if the products were endothermic, the reaction was endothermic, the value of energy of products would have been quite high. In that case, you would find that it would be easier to change the products back into reactants. So those are some generalizations that you can notice here. So a graph representing the energy of activation for a catalyzed reaction and uncatalyzed reaction, we can give you values on the y-axis and ask you to calculate what is delta H, what is energy of activation for the forward reaction, backward reaction. All of these can be asked. So that is something that we expect at this point. So I think we looked at the definition. A catalyst is a substance that increases the speed of a reaction without itself undergoing any chemical change. So that is one of the important aspects. When we talk about a catalyst, the catalyst, we require a very small quantity for the catalyst. We don't need a large quantity. And at the end of the reaction, usually the catalyst is regenerated. It's never consumed in a reaction. Catalysts are never consumed. It alters the rate of the reaction. It produces changes all the reactants into products. At the end of the reaction, you have the catalyst back. So such a substance usually is what we refer to as a catalyst. Okay. So usually they work by providing alternate paths where the energy of activation gets lowered. Okay. So those are some generalizations and statements that you may want to recall, especially in multiple choice questions. All this information will be handy. We had seen about radiation, so I think we will not talk about radiation because when we looked at zero order reaction, we did talk about that. So I'm going to leave that for now. Probably I included something here. No, okay. There was something. So something I want to talk about catalyst. You're going to do some general reading on catalyst. It's classification of catalyst. So if you look at catalyst, you can classify catalyst, and we will look at a couple of examples. They can be classified into homogeneous catalyst and so this is something that you may want to do some additional reading on. In your textbook, it's actually, the section comes under 14.9. And if you read that full section, you will come across homogeneous and heterogeneous catalyst. You may want to recall some examples for it. Homogeneous catalyst means if the reactants and catalyst are in the same phase. So here, they are in the same phase. And heterogeneous, reactants and catalysts in different phases. You should be able to come up with at least one example. So this is my suggestion. Manufacture of sulfuric acid. Sulfur is allowed to react with oxygen to change into SO2. Again, SO2 is changed into SO3. That is an oxidation process. And then SO3 is absorbed in water. SO3 is absorbed in water. It gives you H2SO4. So that's how you produce sulfuric acid. Or theoretically, these are the steps. You take sulfur, burn it in air, it produces sulfur dioxide. The second step, changing sulfur dioxide to sulfur trioxide, that's a little bit difficult. It takes a little bit more energy. For that reason, we need to use a catalyst for that reaction. Now, there are two methods. One is a contact process, and the other is the more recent method that we use. We use vanadium pentoxide as a catalyst there. That's kind of a heterogeneous reaction. But we are going to talk about the homogeneous catalyst here, which is nitrogen dioxide, which is used as a catalyst. So this reaction mixture is in a closed system. We bring in the sulfur dioxide, add a little bit of nitrogen dioxide, which is actually a brown colored gas. And then the reaction is actually becomes faster because the energy of activation for the second reaction actually is lowered. So the rate of reaction increases and we get a larger quantity of sulfur trioxide, which can either be dissolved in water. In reality, it is dissolved in sulfuric acid when it produces a compound called oleum. So if you just add H2SO4 to SO3, the product that you get when you add that is called oleum. Oleum is a highly oily liquid, very reactive. If you normally for producing sulfuric acid, you dilute it quantitatively, and that's how you obtain sulfuric acid. So here, for simplicity, we said it can be dissolved in water to produce sulfuric acid. So on the left side, where we see the homogeneous catalyst, we're going to look at this reaction where we're going to use the catalyst. NO2 is the catalyst that we're going to use. Okay. So let's write an equation. It's actually, also in your textbook. So SO2 plus NO2 gives you SO3 plus NO. Now, NO plus half O2 gives you NO2. So NO and NO cancels out. NO2 and NO2 again cancels out. So the reaction changes into SO2 well, it's not letting me write there. Okay. So I'm going to rewrite it over here. So that is the step. So the second step, where we produce sulfur trioxide by oxidizing it in the presence of nitrogen dioxide, which is a catalyst. So you'll find that sulfur dioxide, nitrogen dioxide, nitric oxide, all of these reactants and products, including the catalyst, are gases. Therefore, this is a very good example of a homogeneous catalyst. And you'll notice something. We actually wrote a simple mechanism for this reaction involving the catalyst. And you would notice that nitric oxide is produced in the first step. And this is consumed here. So nitric oxide is one substance that is produced in the first equation and consumed in the second equation. So we're going to call it something. Any substance, while we are writing a simple mechanism, that which is produced in one step and is consumed in a subsequent step would be called a reactive intermediate. So this word is important because we can give you a set of mechanism or equations. We call those steps elementary steps. So we have two elementary steps here. The first one is SO2 plus NO2 giving you SO3 plus NO. And the second one is NO2 plus half O2 giving you NO2. So there are two elementary steps in this reaction. And in the first elementary step, we produce nitric oxide. We are going to call it a reactive intermediate because that's going to be consumed in the second reaction. So the definition of a reactive intermediate is it has to be produced in one of the steps and it should be consumed in one of the subsequent steps. It will never appear in the final equation for the reaction. So we have defined one of the substances that doesn't appear in the final equation but is also part of the reaction system. Now at the same time, we have a second substance which doesn't show up. That is nitrogen dioxide. Nitrogen dioxide is actually a reactant to start with and ends up being a product. So you'll see that there are two substances that do not show up in the final equation, yet they are in the different elementary steps. One of them is always a product and then gets consumed. The other is a reactant that is changing into a product and finally they get cancelled out. Therefore, nitrogen dioxide is considered a catalyst. Catalyst has to be added at the beginning of the reaction and it will be regenerated at the end of the reaction. So in reality, you will still have the amount of nitrogen dioxide that was added at the beginning. Hence, it behaves like a catalyst. So expectation is you should be able to identify a reactive intermediate. You should be able to identify a catalyst if a mechanism is provided for you. So that's one of the important things. So if you look at the different words that you have seen homogeneous catalyst, heterogeneous catalyst, mechanism of reaction, of which here we have two elementary steps. Each of those steps are called elementary step. Now in the elementary step, if a substance is produced in one step and then it gets consumed in the second step, then it is referred to as a reactive intermediate. And if you're adding a catalyst, it will show up in one of the first reactions as a reactant, and it will end up being a product in another step. Therefore, we can cancel out the reactant and product. So we can identify a catalyst from the mechanism of a reaction if it's provided. Okay, so these are some of the things that you may want to recall in terms of the catalyst and the definition of homogeneous catalyst. And so there will be practical application questions by merely expecting you to identify it rather than define it. Okay. So homogeneous catalyst, there are so many gas phase reactions or aqueous solution phase reactions, then we will use these. Now we also have heterogeneous catalyst. Heterogeneous catalyst, the reactants and the catalyst are in different phases, which means different physical states. One common example for that would be the production of ammonia, the Haber process. It would be a good idea to read about the Haber process because that keeps coming back over and over again, not only in rates of reaction or chemical kinetics. When we are studying chemical equilibrium, that's a very popular example. So you may want to look up the Haber process. The other industrial method for the manufacture of a compound is sulfuric acid, which we had just seen right now. That is the contact process, and the lead chamber processes are the two processes that are available. One of them involves a solid catalyst. The other involves only gas phase reactants and products, including catalyst, therefore homogeneous catalyst. So we look at heterogeneous catalyst. The example would be manufacture of ammonia, N2 gas plus 3H2 gas. We should be writing reversible at this point of time, 2NH3. And the catalyst that we use is platinum. We can use platinum, you can use vanadium, you can use vanadium pentoxide, so many different metals. But generally speaking, transition metals are very good catalysts. For most of the industrial processes, you'll find that a lot of transition metals are used. So when you're studying the periodic table, one of the applications of metals, especially transition metals, would be acting as a catalyst. The reason is pretty simple. The d orbitals are incompletely filled, so they have empty orbitals, and usually they have very high charge, and the nuclear charge is pretty high on moving from left to right. Therefore, the ability for these atoms to actually attract electrons is pretty high. Therefore, for that reason, transition metals are really good catalysts. But platinum, again, is a commonly used catalyst for so many reactions, and it's an expensive metal. So poisoning is kind of limited here, unlike other compounds. Therefore, if you can use platinum, well and good. So here, this is a heterogeneous catalyst. There is an interesting diagram in your book, which you should be looking at. It's on page, if you look at 682, on the top left hand, you have a nice depiction of how the reaction takes place, how the gases react with the solid phase, and that's an interesting reaction that you may want to look at. Now, there are two words here. Can anybody give me a difference between the two? One is absorption and the other is adsorption. Any clue as to what's the difference between these two words? Have you come across this word, or we change the B to a D, and we have a different phenomenon altogether in the branch of chemistry that deals with so many aspects of the physical interactions. So absorption is obvious. You take a sponge and put it on water, and it absorbs all the water goes into it. Now, if you actually go to a classroom where we have these blackboards, and you know that after writing with chalk, there is a lot of chalk dust that is on the blackboard. Is it going into the blackboard? No, it's only on the surface. Because if you actually use some nice remover, you can just usually paper with moist paper, you can wipe it off. Now, when you go on vacation, if you usually close all your house, you lock your house, you put all your your furniture, you really have to cover it with stuff. If not, you'll find there is a lot of dust that accumulates on it. The dust not only accumulates on your furniture, but even on the walls. The walls are vertical, but still you'll find that there is dust attached to it. So what causes this phenomenon? So here is a new branch of chemistry. It's called adsorption. Adsorption is a surface phenomena. It's the ability of particles to attract to surfaces, and there are physical forces of attraction here. So there are two kinds of concepts that I talked about there. One is called physisorption. Which means physical absorption, and the other is called chemisorption, which is a chemical absorption, you can say. They are in chemisorption, there is kind of when you can calculate the delta H for the changes that are happening there, which is kind of most larger than physisorption. Physisorption is a weak attraction. It's like physical attraction versus chemical attraction. That's what it is. So there is a branch of chemistry that deals with it. So every time we are looking at a heterogeneous catalyst, the catalyst, if it's a solid, actually enhances the ability of the reactants to come close together, lower the potential energy, and undergo a chemical change. That's the basis of it. So if a chemical reaction has to take place, we have to lower the energy of activation. The other aspect is the reactants should come close to each other. There should be a physical proximity for the reactants. Only then there can be a bond formation. So what a catalyst does is, because of its ability to undergo adsorption, it will attract both nitrogen and hydrogen towards itself. And these very high positively charged metal cores tend to attract the electrons in these gas phase molecules and attract them closer to the surface, which means brings the molecules closer together. When the molecules come closer together, the second thing that happens is they start donating their electrons to these empty orbitals or to the positive charges by forming weak attractions, which means the bonds between the atom tends to get weakened when this happens. And that's what makes it easy for the molecules to break the bonds and form new bonds. Therefore, look at the diagram that is given in your textbook 682. That's a pretty interesting diagram where it shows the concept of reactant gas molecules being attracted to the metal surface, and the actual phenomena that takes place is adsorption, and adsorption helps in lowering the potential energy, and then it also weakens the bonds between the diatomic molecules, making it easier to break and form new bonds. So those are some of the things that happen. So we have catalyst, homogeneous catalyst, heterogeneous catalyst. And another example is in all of your cars, you have a catalytic converter, and it's supposed to have a little bit of platinum in it. Then it will last for a long time and actually converts all the incomplete combustion gases, the oxides, back into their natural state. So that's what it's supposed to do. So always having a very good catalytic converter makes it environmentally safe, which means you won't be polluting the atmosphere. So a lot of practical applications for these catalysts and the different types of catalysts. So do a general reading, practical applications. There are also industrial production of many of the commonly needed chemicals which use a lot of catalyst, whereby we are trying to make the process more and more efficient. So those are some general aspects. Now, one other thing that I want to talk about is there is another type of catalyst that is called an autocatalyst. Now, the equation I'm going to write, even though it looks a little bit complex, so I've written it once or twice. When you learn electrochemistry, you're going to learn the balancing of those equations, and it's going to be pretty simple and straightforward. Let's take two examples. One is Fe2 plus Aq reacting with MnO4 minus permanganate ion. I should write the M right. Plus acid gives you Mn2 plus Aq plus Fe3 plus Aq plus 4H2O. This is a balanced version of the equation. You don't need to balance it here. So here you have, this is a purple colored liquid, KMnO4, potassium permanganate. You may have come across it because it's also an antiseptic. So iron, Fe2 plus, reacts with permanganate ion to form Fe3 plus. So the oxidation number of iron is changing from 2 plus to 3 plus. Manganese is the oxidizing agent. It will change from +7 to +2. We will learn that later in electrochemistry. Don't be worried about that. Now, this reaction, so I can prepare Fe3 plus by using iron nitrate. I can prepare permanganate ions by dissolving potassium permanganate in water. And if I add potassium or iron to potassium permanganate, this is pink in color or purple. And the manganese here is clear, colorless. There will be a color change, immediate color change at room temperature. That's important. This reaction takes place at room temperature. It's instantaneous. It's almost an ionic reaction, just like an ionic reaction, maybe a little longer than a double displacement reaction, which you have seen between silver ions and chloride ions, but the reaction does take place. The visible change is potassium permanganate. The pink color is lost when all of the manganate ions react with Fe2 plus. This happens really quick in class. You can actually perform a lab. Normally we do a lab for it. The reaction between iron solution permanganate in redox titrations. If we get a chance, that's what we will do. So that's a quick reaction. But on the other hand, if I use C2O4, we talked about this again Aq, and we allow it to react with MnO4 minus plus H positive, giving you CO2 gas plus Mn2 plus H2O. It's not balanced. So again, you're getting Mn2 plus here and Mn2 plus here. So the pink colored substance will lose its color. Now this is what happens. If you add oxalate, which is coming from oxalic acid, the formula for oxalic acid is H2C2O4. So if you dissociate it in water, it gives you C2O4 2 minus, which is a dicarboxylic acid. So if you take this oxalate or oxalic acid and add it to potassium permanganate at room temperature, the reaction is very, 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 very slow. After about 10-15 minutes, it will change into a slightly brown colored solution. That reaction is never complete. And it will continue to be brown in color for quite a... There is some change taking place, but the color would not change rapidly. On the other hand, if you heat it to about 70 degrees Celsius and allow the titration to take place, it changes color immediately. And one of the other things that you notice is, initially, for the color change to happen, when you add oxalic acid to permanganate, it takes a little bit of a time. But once the color change happens, the reaction is extremely fast. Just like in the first reaction between Fe2 plus and MnO4, the second reaction that I've written here will also become fast. So here, the only reason that the reaction becomes fast after the initial reaction being started is that the product formed, in this case Mn2 plus, becomes a catalyst in the reaction. So there are certain chemical reactions where the product formed becomes a catalyst. So if the product is formed and if it acts as a catalyst, then it lowers the energy of activation, the mechanism is altered, and the rate of reaction will be fast. Such reactions where the products formed can behave like a catalyst is referred to as an autocatalyst. So here Mn2 plus is an autocatalyst. So if you take oxalic acid and permanganate and allow it to react, instead of heating, you can add a little bit of manganese sulfate, which contains Mn2 plus. So the rate of reaction will be slightly faster than at room temperature. But again, once the reaction is initiated, it continues really, really fast. So all that you need to know is what is an autocatalyst. And this is the best example. At this point, I'm not asking you to memorize that equation. Later, you'll find that once you've done the balancing using oxidation number and the ion electron method, you'll be fine with that. So we learned about catalyst, homogeneous catalyst, heterogeneous catalyst. We saw one example each. If you can find out more examples, that'll be nice. A lot of industrial applications here. And then finally, we talked about autocatalyst. So autocatalysts are substances that are produced, are the byproducts of a reaction which catalyzes the reaction. Therefore, the rate of reaction tends to increase. So a number of new words here. We talked about mechanism of reactions involving catalyst. There we identified the term reactive intermediate. We talked about the catalyst, how we can identify from a reaction. So when you add up the reactions, you don't find either the reactive intermediate or the catalyst in the reaction. Those are some of the things. Again, how do they function? Catalysts, they lower the energy of activation. And the second aspect that we see happening is during the use of heterogeneous catalysts, they lower the energy, bring the reactants together by a phenomenon called adsorption. Those who are interested, read more about adsorption. There is a branch of chemistry itself dealing with adsorption. So it'll be a nice area to delve into if you're interested in those topics. So that's regarding catalyst. So here again, we want to talk a little bit about graphing and mechanism. So if you look at this graph, there are 3 peaks in it. So how many steps, how many elementary steps in this reaction? That's what we need to know. Is there a mechanism involved for this reaction? So if I give you this graph, does it represent a reaction that involves mechanism? That's the first thing that you should be able to deduce. If that's the case, how many steps are involved in it? If I know how many steps are involved, you should be able to say which steps are faster and which is the slowest. That is something that you should be able to say. So if anybody wants to tell me whether this is a multi-step reaction, what type of reaction could it be, which reaction is faster, which reaction is slower. These are some of the things that you may want. So I have made a worksheet for you. I've posted it under mechanism. You can actually you can type it in, save that file, and then you can upload it back. So again, this is something that you may want to look at. If you have a single peak in a graph like this, it means there is a single step reaction, which means the law of mass action and rate law is the same. If you look at this graph for the energy with respect to the reaction coordinate, you'll find that there are 3 peaks involved in it. So the reaction, we have the reactants at this point. This is where you have the reactants, and the final products you have over here. But again, in between you have reactive intermediates. A is the reactive intermediate that is formed here before it changes to some intermediate at this point, which I'm not labeled there. And then you can change this particular reactant into something else over here, and we have the second reactive intermediate over here. A, B, and C are the 3 reactive intermediates that we have in the 3 elementary steps that are taking place in the reaction. So in this reaction, there are 3 elementary steps. So if you have to write an equation, you can write 3 equations. When you add it up, you get the net reaction. And then if you look at the 3 values for the energy of activation, we have D over here, we have E over here, and G over here. You know that E is the largest. E is the largest. D and G are smaller than E. That's all that we need to know here. Therefore, the second step is the slowest step. So if a mechanism is given to you, you need to identify the slowest step, because the slowest step is the rate determining step. The rate determining step is the slowest step, which means the slowest step has the largest energy of activation. So if you have the numerical values, you can say which step would be. So we can write three equations. The second equation in this case would have the largest energy of activation. Therefore, that would be the slowest step. If you have the slowest step or the rate determining step, then you can write the rate law purely by looking at the reactance on it. That's a simplified version of it. Okay, there are more complex cases where the slowest step may also have a reactive intermediate where we can eliminate it by adding a different constant and solving for it. But we're not looking at it at this point of time. So here, what we're going to say is, in certain reactions, if there is a mechanism involved, each of the steps can be represented by a single peak as part of the net reaction. So in this case, the first step has a reasonably small energy of activation. It easily changes to a product, and that changes into the next product. The energy of activation is much higher. That requires a larger amount of energy. So that reaction will be a slower reaction. And in the final case, the energy of activation is again small, just like D, almost close to D. So that is also a quick reaction. So 3 peaks, 3 transition states, and 3 energy of activation. And you can also calculate energy of activation for the forward reaction, energy of activation for the backward reaction, to know which would be more stable, etc. So you should be able to identify the different letters in the different peaks, and also calculate the value of delta H from the reaction. That will tell you whether the reaction is exothermic or endothermic, how many steps are there. And you can also write a mechanism, or if the mechanism was already given, identify the slowest step and write the rate law from it. Okay, so this graph is important. You're expected to either draw it or make an interpretation from the graph that you get. Okay, so there is a worksheet that I've already posted for you. So if there are any, I just made it. If there are any errors on it, just make a note of it and let me know so that I can make corrections for that. That's one thing. So just to get some general idea about mechanisms. So here we have a question here which says the reaction CO plus NO2 gives CO2 plus NO is second order in NO2 and 0 order in CO. Is the following mechanism consistent with this information? So I've added a sheet on Brightspace where you should be able to see the rules and requirements for writing the mechanism. Let me see if I can show it to you. I posted some lesson notes here with the graphs, and if you look at this point, some simple questions. When will you suggest a mechanism for a reaction? So these are the requirements that you need to bear in mind before answering those questions. So just to generalize it, there's a lot of stuff written in a textbook, so I just try to crystallize it to give you what you need. When you suggest a mechanism for the reaction, this is what you're looking at. If the rate law and law of mass action are different, which means order and molecularity are different, you would say that there's probably a mechanism involved in the reaction. Okay, so that's the first thing. So you will look at the reaction. If you have numbers where you can calculate the rate law, identify the order of the reaction, look at the balanced equation, and if the balanced equation, if the sum of the coefficients of the reactants is different from the overall order of the reaction from the rate law, then you would say that the reaction involves a mechanism. That's what it means by that. Okay, so you need some information for making that prediction. Then again, what are elementary steps in a mechanism? The steps that we tend to write so that we are suggesting possible ways in which the reaction is taking place. Now, what it also means is we just cannot look at the reaction and say that this may be the method. First, we theoretically suggest a possible mechanism. Then you perform an experiment and try to identify the reactive intermediates that may form in the reaction. So if you're suggesting a theoretical mechanism, you will expect certain products to be formed. So then what you would do is you would design an experiment to identify those reactive intermediates. So if by a chemical reaction you can prove the existence of the reactive intermediate, then you can say your mechanism may be probably right. So that's the way we proceed with reaction mechanisms. So a lot of experimentation has to be done. We have to look at these aspects of mechanism. What are the elementary steps involved? What are reactive intermediates? So we have the reactive intermediates there. So that's the next part. What are reactive intermediates? Reactive intermediates are substances that are produced in one step and consumed. So that's what we'll be looking for. Again, what happens to the reactive intermediates? They get used up in the subsequent steps. And finally, what do you mean by why is the slowest step important in determining the rate of reaction? Because the fast reactions will take place, but like in the previous graph that you had seen, if you want to get to the third stage or third elementary step, the second step has to happen and produce its product. And that requires quite some time. So even though the third step is faster, the rate of formation according to the third step depends on how much of the reactants are coming from the second step. Therefore, for that reason, the slowest step is always the rate determining step. And that's how we actually make our final conclusions. So these are some ideas that you have here, which you can actually look at while predicting mechanism of reaction. So we will look at the simple problems that are given here and see what it means. So here we have the reaction carbon monoxide and nitrogen dioxide giving you carbon dioxide and nitric oxide is second order in NO2 and zero order in CO. Is the following mechanism consistent with the information? So because they are already given you the value for the order of nitric oxide and carbon monoxide, you can write a rate law, right? Rate would be is equals to K into concentration of NO2 raised to 2 into concentration of CO raised to 1 or raised to 0. So this doesn't count, right? This reactant doesn't count. So again, rate determining step is the slowest step. So this is the RDS, rate determining step. So if you write the rate law according to this one, this would be rate is equals to K into NO2 raised to 2 based on this equation. Therefore, the observation or one of the things that we can say is the slowest step is a rate determining step. And if you look at the reactants, that is in agreement with the observed fact based on the calculation. That's one of the things that you can do. Okay. The second aspect that you have is you have to actually add up these equations. When you add up all these three, what do you get? So you have, let's say, N2 over here, N2 over here, you can cancel that out. You have 2 O2 here. You have 1 O2, 2 O2. So this and this cancels, and this goes away. Again, what else is there? You have CO2 here, but there's no CO2. So we're going to rewrite the equation. That would be 2 NO2 plus 2 CO giving you 2 CO2 plus 2 NO. Okay, so this is what we have. Yes, so if you divide this by 2, 2, 2 and 2, you have the required equation. So in this case, the mechanism suggested satisfies the conditions. So earlier we said, what are the conditions? Whenever we have the different elementary steps that are given to us, when you add them up, you should get the net reaction. The second condition is the slowest step, which is a rate determining step, should have the order as calculated from an experimental evidence. So in this case, both of those values are satisfied, and for that reason, we can say this mechanism is acceptable. Okay, so that's how you will be answering these questions. So just to give you an idea, so the sheet that I showed you, the Word document that I posted there, that should give you some general ideas to how you will be proceeding in terms of answering these questions. Yeah, I just stated it right now. The rate law is written. The rate law is consistent with the data given to the problem. Adding the elementary steps gives us the original equation. the mechanism is acceptable because the slowest step also has 2 NO2 as the concentration of the reactant.